So, we'll have our problem session as always tomorrow. And I think I will remind you that we're going to have our problem session on Friday morning next week. Have to find a room for that, right? All right, very good then. So, let's pick up where we were. So, we're talking about the idea of entanglement, something which I expect you've seen in some previous courses, but I want to review today as well. So what entanglement is about quantum correlations between different degrees of freedom, okay? And those quantum correlations can be quite different. Some people think it's the whole story of what makes quantum mechanics different from classical physics. You know, it's interesting when we have these different features, and it's how there's a long analysis and study of the interrelationship between the different features, such as the fact that things don't commute, or so-called contextuality of outcomes, and negativity in quasi-probabilities and entanglement. Are they all the same thing? Are they related to one another? Interesting question. Maybe we'll touch on that a little bit. All right, so when we mean by correlations is about statistical correlations. So if we're thinking about it in classical physics, if we have some random variables, we say that those outcomes are statistically independent if the joint probability distribution factorizes. Then we say that those two outcomes are statistically independent from one another. Quantumly, in particular, if we have a pure state that is described by, say, some wave function associated with those continuous variables, then, of course, this is the rule for the probability distribution, and thus statistical independence is equivalent to saying that the wave function factorizes. If it does, then we say that the state of the system is separable. Okay. Otherwise, we say it's entangled. So for a pure state, we have a choice. Either we have statistical independence, we have separability, or we have the state is entangled. There's this whole subtle and very complicated business if the joint state of the system is mixed. If the joint state of the system is mixed, we can have the situation where it's not, where we have correlations, where we have statistical correlations, but we don't have entanglement. Entanglement and statistical correlations are not one and the same thing. They're only one and the same thing if the overall state of the system is pure.
The Schmidt particle is not quantum.
What's that?
The Schmidt particle is not quantum.
It is not. That state is not quantum. In particular, if we have a state of the joint system which can be written in this form as a statistical mixture of product states, that state is generally called separable. Even though it's not a product state, it's just unfortunate that's the language we use. I don't like that word. I prefer to call it unentangled, okay? It's unentangled, meaning it has a perfectly good classical description in terms of those correlations, in terms of this classical probability distribution. If this doesn't factorize, then we have classical correlations, okay? And quantifying the amount of entanglement in a mixed state is a complicated beast. And there was a decade of work on that. I don't know if it's things that you've seen or studied in some of your other quantum information courses, some of you in the past. All right, so what are some of the important features? Why do we care? Why is entanglement interesting? Why is it weird? Why is it important? So one of the features that we talked about last time is the notion of information and where the information is. If we have a entangled state, then the information is stored in the whole and not in the parts, okay? So in particular, if we have a pure state of the joint system, that system, it has zero entropy, meaning there is no missing information that we could have in principle to more completely define the state. It doesn't mean that every measurement outcome will be determined, because that's, well, we'll talk more about that whole story in a moment. That's the kind of craziness of quantum mechanics. But nonetheless, this state is the maximum information we could possibly have and define it. Nonetheless, doesn't mean that when the state is entangled that we know everything about the parts. In fact, we have a lot of missing information about the state of a subsystem or a part of the system. So as we discussed and reminded ourselves, if I want to look at the state of subsystem A, irrespective of what is measured on B, then we marginalize the state. And that means we do the partial trace. We trace out, as we say, one of the degrees of freedom, and that gives us the reduced density operator. I prefer to call it the marginal, because it is what it is. I think that's the right way to talk about it. Similarly, we can marginalize and trace out A, and given a pure state of the joint system, this thing is pure, the marginals are pure if and only if the state was separable, okay? So if the state is not separable, if it is entangled and is a pure state, then the amount of entanglement is completely quantified by how mixed the subsystems are, okay? How much information is missing in the state of the subsystem is how we define entanglement. And the way we quantify information is through entropy. That's the Shannon definition, generalized here. This is the von Neumann entropy. The von Neumann entropy is a property of the state, and the entropy could be zero for a pure state, and this for the maximally mixed, where we have absolutely no information at all, okay, about which of those outcomes are, okay? And so that's how we define the amount, that's how we quantify entanglement, is by that missing information. So that's one of the important properties. Again, as I said, if the state is mixed, then we have to ask ourselves, well, can the state be written in this form? If it can, then there is no entanglement. Yet, of course, the marginals have entropy, but that entropy was due to the missing information of the whole. It wasn't due to entanglement, okay? So how we define entanglement for mixed states is a complicated beast, and we can talk about it offline another time. So it'll take us weeks to really do that. Do you guys talk about that in muscle? Yeah, he does that. It's hard. It's a hard problem. Even for two, you talk about the entanglement of formation and bound entanglement and all that stuff. Yeah, anyway. interesting. Okay. So I just want to mention, entanglement as a resource for information processing. We won't talk, maybe we'll see what we have time to do. We won't talk a lot about this, but some of you I know have studied the idea of resource theory, and sort of the original idea of resource theory came from thinking about entanglement as a resource. And what kind of a resource is it? It's a resource for quantum communication. And first and foremost amongst that is quantum teleportation. So quantum teleportation is a protocol by which information can be transferred between remote parties if they shared entanglement between them. Okay. So how much teleportation we can do depends on how much entanglement. So I could have a mixed state of the kind I mentioned before, a separable state that still has entanglement that I can still use for teleportation. And how much entanglement is in that is one way of quantifying the amount of entanglement of a mixed state, is how many bits of can I teleport. More recently, what's interesting is quantum metrology or sensing beyond the so-called standard quantum limit. Maybe we'll talk a little bit more about this, but the idea that if we have an entangled source that we could use to probe a system, then having entanglement can be a resource that allows us to have a higher precision in our measurement than could be allowed if we had unentangled particles. And then finally, quantum computation. This is an interesting story, and one that goes back many decades now. I mean, almost every paper that was written for decades was entanglement is the most important resource for quantum computation. But it's a very subtle story. It is certainly true that if our quantum computer had no noise and was a pure state, then we could not do a quantum computation better than we could do classically unless the state was entangled. And so there's a direct relationship sort of between the computational power and entanglement. But if we have a noisy system, then it's far from clear. I could have a state which is noisy and maybe doesn't have that much entanglement, but still would be powerful for quantum computation. So other measures of quantum correlations, entanglement's not the only measure. There are other information theoretic measures that are based on mutual information and so-called quantum discord and other ways that we think about it. But nonetheless, we do think about just generally entanglement as a resource. Okay. So I want to maybe quantify this a little bit more. In the simplest case we can, in some sense the most important case, where the overall system is pure. Okay, so I want to think about that and quantification in the relation to the von Neumann entropy, which is our way of quantifying entanglement for pure states. Okay. So let's just start with just a little example here. let's say I have 2 qubits. Let's say spin 1/2 particles. And let me look at the following joint state of the system. Is that an entangled state? It's not, it kind of looks like it, right? It doesn't look like it. But in fact, this state is equal to that. Tensor product, yeah. This is something we're often sloppy about, and we don't, we ultimately write, I can write, these are all different things. This is equal to this is equal to this. We're sloppy in different ways. Okay? Right? So this state is separable. I just made it that way, right? So this state is spin up along y times spin up along x. It's not obvious by just looking at this whether it was separable or not. So we need a way of, without having to, oh, look, can I factorize it and try to do it, especially when I have more than a two-dimensional Hilbert space, to be able to quantify how much entanglement is in the system without having to guess in this way. And so that brings us to the story of the Schmidt decomposition. All right. The Schmidt decomposition is the whole story in the way in which we should think about entanglement, bipartite entanglement of pure states, okay? So this quantifies entanglement for bipartite systems. How does it work? Okay, so let's say, consider a joint Hilbert space of 2 subsystems, a bipartite system, where this has some dimension d sub a, and this has some dimension d sub b, so that the joint system has a dimension that's the product of the two, okay? And let's say that I have some basis for subsystem A and a basis for subsystem B. By the way, these could be infinity. I could have infinite dimensional cases too. So if these are bases for the 2 Hilbert space, then we know that Ij is a basis for the joint space, and I can take any pure state that is in the joint Hilbert space and expand it in the spaces, okay? So this is the sum I equals 1 to d sub a, j equals 1 to d sub b. Some probability amplitudes I'll call gamma ij, ei fj. Okay, So these are the probability amplitudes in the basis. Okay? And we want to see, is the state entangled and how entangled it is. Okay? And what the Schmidt decomposition, I'll just state what it is and then we'll prove it very quickly, states, is that this is equal to the following thing. It's a sum over at some index, I'll call mu, up to some mu max, I'll call chi, times some, let's see, what notation do I want to use here? Okay, good. Lambda mu, u sub mu on A tensor v sub mu on B. Okay? So the Schmidt decomposition says any state can be written this way, where chi is between 1 and the minimum of dA times or dB, okay? And it's known as the Schmidt rank of the state, this parameter chi. And these are positive numbers, which are not zero because the ones that if we allowed zero, this sum would go bigger. Okay, so these are non-zero, they're all positive numbers, which are known as the Schmidt coefficients. And these vectors are orthonormal. And they're known as the Schmidt vectors. So the Schmidt decomposition theorem tells me, and we'll prove it in a moment, that any state can be written in this manner. And it has some very interesting implications, okay? So my first question to you is, what are the marginal states in this context? Given the Schmidt decomposition, what is the marginal, say, rho sub A? How would you find it? You do a partial trace. So I take the outer product of this with itself and trace out, and what do I get? I have a sum over mu, lambda mu squared. Does everyone see that?
Do you need to normalize it?
No. When you do the partial, why is this? So let's just quickly write this on the side here. What is rho A B? It's the outer product of this with itself, which is a sum over mu and mu prime, lambda mu times lambda mu prime, u mu A prime tensor v mu prime b. Everyone agree with that? So now I'm going to do the partial trace. This thing is the partial trace over subsystem B of the joint system. So how do I do the partial trace? I do the trace over this guy. And what is that?
Delta mu prime.
That motion means one, but
It means you take the outer product and you turn it into an inner product. That's how you take the trace, right? And what is that? It's a delta function. You prime, and so you get that. Beautiful. What about the marginal of subsystem B?
Lambda mu squared.
Same thing, but with different set of eigenvectors.
With the same eigen.
But the same eigenvalues. These are the probability of C, these are the eigenvectors, or I'm sorry, the eigenvalues of the density operator, and they're positive numbers in this case. And so what we see, interestingly, is a few facts that arise from this. So what this tells us is that the spectrum of row A and row B is the same. Which means that the entanglement can be equally found by either looking at the entropy of row A or the entropy of row B. They have the same entropy because they have the same spectrum, and the spectrum determines the entropy. And it's determined by the Schmidt coefficients. So the Schmidt coefficients tell me what the entanglement is. And the Schmidt rank is the poor man's version of the entanglement. You can just say, oh, the number of non-zero rows is some measure, I'm sorry, it's non-zero p mu's is some measure of how entangled it was, because it tells me something about, you know, how much this contributes. But it's not a very good measure, because I could have some of those items be 10 to the minus 14, and they're not really contributing. I could have a full rank, this being at its maximum value, and some of those Schmidt coefficients can be absolutely tiny. It's better to look at the entropy as a way of measuring.
So, subsystem B has a certain entropy, and say it is not the minimum entropy. Say A has a smaller dimension than subsystem B. If I marginalize A, then I get PB, but it has dimension of Hilbert space A.
Okay, good question, and let me try to unpack that a little bit. So, we have two subsystems, and you're right, they need not be the same dimension. This might be a qubit, this could be a qtrit, for example, okay? So, in principle, I could have a mixed state of subsystem B, which has more entropy than subsystem A, because I have more choices and more information in some sense. As we said, the maximum amount is the log of the dimension. However, we're talking about something that's a little bit counterintuitive and different, which is we are not allowing for entropy to be in either of these systems independently. The entropy is in the entanglement. So the joint system here is pure. I can't have a lot of entropy to start thinking about, oh, a product state where I have this much entropy in A and this much in B, I have this overall pure state. And what we find, based on the Schmidt decomposition theorem, is that the entropy of the two subsystems must be the same if they came from an overall pure state. Okay? Yeah?
Isn't that, since we've already kind of established that entropy and entanglement are be pure states is like
One and the same.
one and the same. So the fact that the entropy of A entangled with B and the entropy of B entangled with A, should, like that.
It's not
seems-
crazy, not crazy,
Okay.
yeah, not crazy. You would say that's what you expect to have true. But it's also true, what Benny said is that if I didn't start with this overall pure state, I could have separate, I could have different entropy in the subsystems. I
But we
could have-
established that the entropy of a mixed state is always funky.
It's how we unentangle entanglement from classical correlations in mixed states is a complicated beast. Yeah. All right, interesting. Okay, so that's an important thing. The other thing that we see here is that the Schmidt vectors are the eigenvectors of the reduced density matrix. So in principle, it looks like I could, instead of doing the Schmidt decomposition, I could just marginalize and find row A, diagonalize it, find its eigenvalues and eigenvectors, and similarly do the same for B. We find the same spectrum but a different set of eigenvectors generally, and thus it seems like I could reconstruct the state, the joint state, from the marginals. But we just said that we can't do that because there's missing information in the marginals that's not in the joint state. So why doesn't this work?
Can we actually make this? Is this the difference between finding the state versus making it?
No, it's just, this is a piece of math.
Okay.
The question is, if I do the marginalization by just taking the state, like this one, tracing out one of the subsystems, diagonalize it, find its eigenvalues and eigenvectors. Do the same thing for marginalize, trace out A, find the eigenvalues and eigenvectors. Then just, there's the total state. What went wrong? Yes?
Is it
Well,
because
no,
there's like infinite purifications of row A? Like,
well, I mean, it is related to purification. You can think about it that way. Yes, indeed.
is the missing information in the Schmidt vector?
It's in the Schmidt vector. But where? The Schmidt vector, this is the Schmidt vector.
Phase?
The phase. The phase, this, once we have here, we've lost information about the phase of the state. I can multiply the state by any phase, and I get the same, because written as a density operator, there's the information that's lost is what the phase was here. Very subtle. And importantly, in the Schmidt decomposition, these are positive numbers, okay? So there might be negative signs and things here. That's absorbed into the definition of these guys. So that's why we need to do the Schmidt decomposition. We want the whole thing. We can't just marginalize them. Because you're close, but not the whole story. Okay, so let me I'm not gonna get into this too much in the weeds, but let's just prove the Schmidt decomposition theorem. So the Schmidt decomposition is equivalent to the singular value decomposition. The singular value decomposition is a piece of linear algebra, which I never learned in my linear algebra class. I don't know if you guys learned. I didn't learn until I had to learn this. I don't know why we don't learn the singular value decomposition, but we should. The singular value decomposition is the generalization of diagonalizing a Hermitian matrix, okay? So let me just quickly say, let's think about, this is the generalization So let's just quickly say a word about that. Suppose I have our Hermitian matrix, and I can think about this as a Hermitian operator, A, which has some matrix elements and some basis, okay? So this is some operator. This operator acts on some Hilbert space and, maps vectors in the Hilbert space onto themselves, okay? If this Hermitian operator, then we know that this operator has a set of eigenvalues, so call them A sub mu. These are the eigenvalues of the operator with eigenvectors, okay? So, I can diagonalize this matrix through a similarity transformation, which is in fact, again, in our case, a unitary transformation. So if I think about it, Aij are the matrix elements of the operator. And if I shove in this set of eigenvectors forms a complete set of operators, I can shove that in over here, that completeness relationship here. Have a sum over mu prime, I, a mu, a mu, a mu prime, j, right? And this thing is a diagonal matrix. I'll call it d mu prime, which has the eigenvalues on the diagonal. And these guys are elements of a unitary matrix, okay? So this is ui mu, and this is the transposed complex conjugate, or u dagger mu prime j. So that's the way in which we diagonalize a Hermitian matrix is I can write that, I can decompose this thing in terms of a unitary transformation on a diagonal matrix, okay? Something we all know. What we're gonna now here is we're gonna think about gamma ij. Those were the coefficients that we can get from expanding in the basis. This is a dA by dB matrix. It's generally a rectangular matrix. It could be a square matrix if the dimensions are the same, okay? And for any such matrix, we can do the generalization of this thing in the following way. Such a matrix can be written, so this matrix in the end we wrote as a diagonal matrix with those of its eigenvectors, right? This thing has the following form. Let's see. Sorry, u sub u a v sub mu b. Okay. So what does this is a matrix that I can think about as not as an operator, where this operator maps Hilbert space B to A, or equivalently, the dagger maps B to A. It's a generalization of a linear map, but the linear map is now between potentially two different Hilbert spaces, okay? And my claim is that the generalization of diagonalization of Hermitian matrix with eigenvalues and eigenvectors like this is something where I have a bi-orthogonal set, where this operator, when it operates on U or V mu B, gives me the eigenvalue, but with its partner, U. Okay, so it's not the same, it gets back with that multiplied by this number, but it flips it, okay? So, let's see if I put this ansatz in the same way, how I can relate the, these biorthogonal vectors and eigenvalues to an effective spectral decomposition of the matrix whose elements are here. Yes?
We're still working with, like, we still have it generalized such that dA and dB can be non-equal in that.
Exactly. So this can be a rectangular matrix.
Okay.
Doesn't have to be a square matrix.
Which means whichever one is bigger will have missing terms. Like, is that mu gonna be the min? The
Well, so at the end of the day, indeed, this thing is this up to this, which is the number of non-zero singular values. So these things are known as the singular values. And those singular values are positive numbers. Okay? So let's see how this works. Okay? So, let's look at this object. That object is equal to, where these guys are, all again, these guys are orthogonal. They're, each one of them, they're orthogonal to themselves within the V's, and the U's are orthogonal with themselves. So if I write this singular value decomposition, this is equal to that. Okay. So, what can we say about these vectors and these numbers? So that what this says is that the U mu's are the eigenvectors of this. And these are the eigenvalues. Similarly, we have this. Yes?
Is this an analog to tracing out a marginal?
It is.
Yeah.
It's the same thing, but now we just see it as as based on the linear algebra of rectangular matrices. Okay, yes?
Because actually, do these have the same dimensions? Like, could we do the commutator of gamma,
I'm sure I
gamma?
have this backwards. I'm sorry, this one, this is this, and this is this. But anyway, I'm sorry, I'm listening.
Like, is the commutator of gamma and gamma dagger physical?
Sure, why not?
Well, do these two have they have the same dimension?
Remember, these are, it's a little bit weird because these are rectangular matrices, right? And so the rectangular matrix doesn't map necessarily the vector space to itself. It maps it to another vector space, which might be a different dimension.
Well, after you do gamma, then it's remission.
It is. And since it's Hermitian, I can diagonalize it. Okay? So,
Is it not diagonalized already? I'm sorry, I might have forgot. The mu, and nu, like two different u vectors are not orthogonal here.
they live in different vector spaces.
I meant like a u1 and u2. Like, is that a basis? Or
This is a basis for Hilbert space A, and this is a basis for Hilbert space B.
Are they orthonormal bases?
Each one, but not with each other, because they live in different
Yeah,
spaces.
but with themselves.
Within
Okay.
themselves, and that's because we see that here. This is a Hermitian matrix, and its eigenvectors can always be made orthonormal. So these guys are the eigenvectors of this, and these guys are the eigenvectors of that. And they're related to one another jointly in this way. So if I have one set of eigenvectors, I can find the other by just applying this vector to that, and I would get the phase right. Okay. So if I apply this to V, I would get mu with that phase, and that would give me the right phase in this case. Okay. That's how you do the singular value decomposition. Once I do that, I see the Schmidt vectors in the following way. So this guy is equal to I E sub I on A, F sub J on B, which is equal to sum over mu, lambda mu, E sub I, U mu, times lambda mu, delta mu, mu prime, V, that's already here, V mu, Fj on B. Okay. So, this is a diagonal matrix whose eigenvalues or whose diagonal elements are the singular values. And what are these guys? Well, these guys are unitary transformations, just like we had over here. This is a capital U on U, and this is a capital V mu J prime. Okay. And so we see the same structure that we saw before.
Should it be V dagger?
Yes, I'm sorry. Let's write it again. This was equal to Fj V mu D, which is the V dagger mu prime J.
What are C and F in this?
F and E were our original basis for the Hilbert space. Okay, so there's some arbitrary bases that we have that we've just chosen some basis. Okay, given that basis, we can expand the state with this probability amplitudes. That set of probability amplitudes can be arranged into a matrix, generally a rectangular matrix. And given that rectangular matrix, we can do a singular value decomposition on it. That singular value decomposition we obtain by diagonalizing these guys. okay? Once we have that, we have a formula that relates these coefficients to the singular values and a unitary transformation that takes me between the basis, the fiducial basis that we started, and the Schmidt vectors, okay? So the bottom line of this is that given a decomposition of the state in any basis, I can always re-express it this way. And once I re-express it that way, I know everything about the entanglement and the marginals. So when we think about entanglement of pure states, we always should think about the Schmidt decomposition, because the Schmidt decomposition is the whole story. If you have the Schmidt decomposition, then you know how much entanglement is in the system, and in principle, what the marginals are. It's the way we quantify entanglement.
So
Yes.
how would you find gamma hat to begin with?
So I define gamma hat as, I have this set of matrix elements, thus now, look at this versus that.
Oh,
This was the state that had the tensor product, okay? This is a linear map that maps, if I operated on Hilbert space B, gives me a state in Hilbert space A, or vice versa. This is the physicist version. For me, writing matrix algebra in Dirac notation allows me to do this. Insert a complete set of states, right? Because now you see these matrix elements are this. Is that clear? So this is a linear map. Any matrix is an operator. But here the operator maps me between two vector spaces. That's why this thing has this funny shape. Yeah.
Is it meaningful to consider the eigenvalues of gamma, like?
What is meaningful is to consider the singular values of gamma. So for any matrix, we can't diagonalize it. If it's a Hermitian matrix, or generally what we say a normal matrix, then we could diagonalize it. But for an arbitrary, n by m matrix, there is no way to diagonalize it. However, we can always write a singular value decomposition, and the singular value decomposition is the moral equivalent of the diagonalization. I just showed you how it's the analogy and how you should think about it as an analogy through it. And it gives us a way of, in principle, writing any, while I can write a Hermitian operator in this way, an arbitrary operator that is maps between two Hilbert spaces has right and left eigenvectors. That's what's different about it. Yes, Nate?
Does it have to be a finite set? Because could we do this with A and A dagger?
Yes, so, well, A and A dagger are not normal operators, so they don't commute for any, but I can always, for any, even if I said dA or dB is infinite dimensional, I can still write a Schmidt decomposition for it, because I have to look at the eigenvalues of A dagger standard in the same way.
What's the condition for normal operators?
A normal operator commutes with its adjoint. So I can't diagonalize A or A dagger, but I can write a simple decomposition for it. All right, yes.
Sorry, I don't mean to take so much time.
Yeah,
Like-
I don't want to go on to
Yeah.
dwell on this forever, but
But
yes.
like you mentioned, like the Schmidt decomposition is the whole story. But at the same time, you also said like looking at the the Schmidt rank is not the whole story with regard to quantifying entanglement.
Right, so what I'm saying is every element in this decomposition tells us everything we need to know. If I just tell you the Schmidt rank, that's not telling you everything. I also want to know what the Schmidt numbers are and what the Schmidt vectors are.
So you need to know all three to truly quantify all
That's
three
right.
entanglement. Okay.
That's correct. That's correct. A poor man's way of quantifying things is just saying, what is chi? Now, maybe one last thing I want to say about this is, if I think about this system and I wanted to say I had, each of these dimensions was extremely huge, okay? And to write out and simulate this system could be incredibly difficult when chi gets very large. But I might approximate the state by truncating some of the singular values. That's a well-known approach we do in thinking about systems like we have many, many qubits and we want to think about this half and that half. And each one of them is exponentially large, it's very hard, but if I don't need to keep all of the entanglement in the system, I might truncate it. Right? And then in that sense, I would say, oh, I keep things up to a certain Schmidt rank. Okay, so that's a whole story about classically approximating complex quantum systems.
Doesn't that have to assume that the earlier Schmidt coefficients contribute more than the later ones?
Absolutely, you'd have to order them in that way. Otherwise, it doesn't make sense. Yes. You'd have to say, I'm going from the largest Schmidt number to the smallest one, and then truncate if they have Schmidt number below some threshold that you choose. All right, very good. All right, well, let's go a little longer, that's fine. Let's continue. So, I mentioned here special properties of entanglement, okay? And one of what we've been concentrating on so far is the idea about missing information and entropy that we see in the mixed, in the marginals that we don't see in the whole. That's a very non-classical feature. But as we know, this whole story of quantum correlations and entanglement is also at the heart of the foundations of quantum mechanics. So, as we all know, we've said before, the idea that the question we have is, in QM, we have effects that have no cause. We intuitively think about cause and effect When something happens, it's because something caused it to happen. And the idea that something happens without any cause to that effect, well, maybe that's just the way the world is, but the question of when that effect comes into being, well, we say when a measurement happens, but what the hell is a measurement? That's, of course, the whole story. That's, of course, Moore said there is when the classical apparatus, but what counts as a classical apparatus versus any other set of degrees? And so it's natural to think that actually there is a cause, but the reason it's random, it's not that it's intrinsically random, but we just don't have access to that cause. It's somewhere in the universe, but it's hidden from us, okay? So, a hidden variable theory there is an underlying cause which is hidden from us. Of course, this is a very natural thing to think. When something is random, it's random not because of something intrinsic, but because there was a hidden variable. Here's a hidden variable, me, right? Okay? Open your hand, close your eyes. Okay, now, it's either orange or blue. What is it gonna be? What's your guess? You don't know. Well, open it up, open your hand.
Orange.
Surprise! You learned something, but this piece of chalk had a color. It's not that the act of measurement caused that color to come into being. It was random because it was hidden from Nate, but it was there. There was a variable, and it was in my head to choose the piece of orange chalk compared to the blue chalk. And so it's natural to think that's what's happening, and that's what Einstein and collaborators wanted to show must be true. That must make sense. And they wanted to show that the quantum mechanical description, because this is hidden for us, it means that quantum mechanics is incomplete. There is a more complete theory if we could figure out what these hidden variables are. Then that we would have determinism once we can complete the theory. Okay? And the famous Einstein-Podolsky-Rosen in 1935 thought experiment brought this into the fore. And it's related, of course, to entanglement. Okay? So their thought experiment was the following experiment. They said, let's imagine, they thought about it from the point of view of position and momentum. Okay? So there's two particles, A and B. They have some position and some momentum. And we want to start with a state that is entangled. Okay? The EPR state that they looked at was not a normalized state, but that's okay. We're okay with that. This is not separable. I can't write it as, I can think about this as the limit of a Gaussian with a very narrow transition, okay? But right now, that's not so important. They thought about it from the point of view of the state that looks like this. If I looked at the momentum space wave function, if I Fourier transform this wave function and look at it in momentum space, then it has the following form. Which is easy enough to take the Fourier transform. Okay? Now, what's special about the EPR state? Well, the EPR state is a simultaneous eigenvector of the relative position and the center of mass momentum of these two particles. Okay? So, if I look at the answer is x0. Everyone see that? Okay, the relative position is x0. The center of mass in this center of mass momentum of these two particles is 0. Okay? It's an eigen, it's centered that. Now, that's fine because the relative coordinate and the center of mass coordinate are two different degrees of freedom, and so they commute. So I can have a state which is simultaneously an eigenstate of the relative position and the center of mass momentum, okay? So they chose it specifically for that reason. A state that was simultaneously an eigenstate of the relative position and the center of mass momentum, which is perfectly legal because these guys commute with one another, okay? So, the Einstein argument for Podolsky and Rosen, probably, is the following. They say, okay, what this tells me thus is, if Alice measures her position and finds XA, then because of the quantum correlations that we have, she predicts Bob particle has position XA plus X0. I guess I worded it slightly. So XA plus X0 minus, yeah. Right, everyone clear on that? And similarly, if she finds PA on her particle, then predicts Bob finds PA equals minus PB. Fine. But the argument thus goes as follows. They define what they wanted to call, EPR defined what they called an element of reality. As real as the color of the chalk that Nate saw when he measured a piece of chalk, which is to say, if without in any way having the possibility of affecting a measurement outcome, one can predict that outcome with 100% certainty, then that outcome corresponds to an element of reality. Let's try to unpack what this is saying, okay? So, we're going to do the Schmidt experiment again, but now, since I don't have blue, I'm going to use green, okay? You ready? Here it is. Close your eyes. Keep them closed. Don't open them. Okay. Open your head and predict and tell the world what the color of, remember they're green and orange.
It's green. The one you have or the one you
I was outside the door. Look, she predicted it. She predicted it was green. And she predicted it was green. I hope you said green. Yeah. And she could predict that she could in no way affect my outcome if we are space-like separated, meaning that there's no signal that Schmidt could have sent to me to affect what mine was. It was green, and I saw it was green when I saw it, not because of Schmidt doing her measurement on her piece of chalk. She could not have affected me, because in order to do so, it would have had to travel, assuming we timed the experiment right, faster than the speed of light. I'd have to go to the other side of the galaxy to make that work, or time the experiment
It's
better.
out of the budget.
Yeah, it's out of the budget. Okay, so that means from this point of view, since Alice can predict what Bob's going to see without in any way affecting what he's going to see, because his measurement happens outside of Alice's light cone, there must have existed as an element of reality that position. And when Bob looked at his particle, he found that position, but Alice in no way affected that outcome, because she can't have affected that outcome because it's outside the light cone in the degree to which we believe that there can be no Einstein causality says we can't affect causes that are space-like separated, things that can only be correlated if they can a signal traveling within the backward light cone. Then we would say that this existed prior to the measurement as an element of reality. Similarly, since Alice can predict Bob's momentum with certainty without in any way affecting Bob's outcome, what momentum Bob will see, then in addition, the momentum of Bob's particle, both his position and his momentum, are elements of reality, which means they must exist in the world as things that are revealed to the observer when they look at them, but they existed. And since both of these things are true, what this says is that XB and PB are both elements of reality. And since they're both elements of reality simultaneously, that contradicts quantum mechanics. Because quantum mechanics says there can't be simultaneously a definite position and a definite momentum that exists in the world. And so they argue that thus, for sure, quantum mechanics is incomplete. That is their argument. It's as simple as that. It makes sense, in my view. Very sensible. Now, Bohr, as I understand the history, said, well, no, because this doesn't make sense. You can't do these measurements. You're not measuring XA and XB. What you're measuring is these two things, and they correspond to a different experiment. And had you done the experiment that measured directly XB, you would disturb the momentum, because we know that position and momentum don't commute, and in the act of measuring one disturbs the other. But Einstein, and I think everyone else who follows, said, oh, that's not fully compelling, because this seems like a very solid argument. That if I can predict the measurement outcome of something that is outside my light cone, then my doing a certain measurement can in no way affect that. So it must have existed in the world, which was just revealed to the observer when they looked at it. And since it's true for both position and momentum, it makes sense. Now, kind of sad, for whatever reason, people threw up their hands, said, shut up, just calculate, use quantum mechanics. I don't know, until, of course, John Bell. And we're going to talk about that next time. I hope to finish it today, but we'll finish it next week. We'll talk about Bell's inequalities. And maybe talk a little bit about some other things that maybe you haven't thought about in Bell's inequalities. How should we interpret? Sorry, I pushed this and it made my phone ring. Sorry. It's my tile, because, I can't remember where anything is anymore, see, so now it does that. But it's in my pocket, so anyway. The story of Bell's inequalities, I still, it's fascinating. What's our takeaway message? What's it telling us? We're gonna rederive it. I think many of you probably already seen it before, but it's good to revisit it again and think about it. Yes, sorry.
Oh, so is the flawed argument that because we're not actually measuring XA minus XB, but rather we're just measuring XA individually, is that the flaw?
Yeah.
I see.
Right. So, when you measure XA, yes, you can learn about XB, but you can't learn about P.
I see.
So did the EPR people fundamentally disagree with Heisenberg's uncertainty principle and say you can measure X and P, but we just don't know how to yet, and that's the hidden variable?
No, I guess it's not that, the uncertainty principle and its implications are empirical facts. So they didn't dispute the facts, they disputed what the fundamental theory was that was leading to that. So the Einstein and his camp believed that randomness was coming from a hidden variable. And those hidden variables are the things that are consistent with the randomness that we see in measurement outcomes, including the way in which a measurement affects a back action. But all of that back action is coming from some other physical effects that are hidden variables.
So what they're really upset about here, like the thing that's Marxist is they were upset that back action appeared to violate the like you could back action something out
Yeah,
here.
and if, yeah, exactly. And that can't be right. If back action is a physical thing, well then it can't actually be true, because then I can affect back action on things outside my life zone. We'll revisit this on Tuesday.
If I could measure XA minus XB, then it is true that I would be able to figure out what that outcome would. But then I would be measuring the joint.
That's right. That's right.
Then it's true that like I could know both at the same
I
time.
do.
But then I would kind of defeat the purpose because I was measuring both at the same time.
Right. But I also but it doesn't contradict quantum mechanics, because I'm allowed to simultaneously measure this and this. But I don't know what XA or XB are. I only know what the difference is.
Individually.
Right. I can measure the difference between XA and XB, but I don't know where XA or XB is. Right? I have to measure only the difference between them. I could do that, and I would get the value x0. It's saying they're separated by this, but I don't know where the center of mass is. Right? And if I have that state, I know where its relative position is. I have no idea where its center of mass is, but then I can completely know where its center of mass momentum is. Because if I have complete uncertainty on the center of mass position, I can have complete certainty on the center of mass momentum. If I have complete certainty on the center of mass momentum, I have no idea where the center of mass is, but I can completely know what its relative position are. But what Einstein and Podolsky and Rosen were saying was, okay, forget about quantum mechanics, I'm just gonna think logically. Logically is, if I measured this and I know what you're gonna get, and I couldn't have affected your outcome because you're outside my life cone, then what you're measuring has nothing to do with my outcome. It must have existed independently of my outcome. Right?
This is like a straw man.
It is. It's a strong. It's a very compelling argument. It makes complete sense.
Somebody at a colloquium once said that while Bohr's response to this was in the long run correct, it wasn't very convincing.
Yeah, for exactly. I mean, it is correct, and Bohr is correct that yes, they're different experiments, but it doesn't get at the heart of the philosophical question. And it was Bell who took the argument this most seriously. And as we saw, it's what's incredibly shocking is that you can actually put this question to a testable experiment, whether or not there exists elements of reality in this way. The fact that you can create a quantitative experiment that you could do to see whether or not elements of reality exist in the way that EPR thought they should is amazing. To be continued. See you next time.
What was Einstein's reaction to the whole